Swayam Prabha. Digital India. Educated India.
Then we discussed about volumetric strain, and then related the volumetric strain to the displacement gradients. Volumetric strain is the fractional change in volume, which is volume after deformation minus volume before deformation by volume before deformation, or change in volume by original volume, something similar to our definition for normal strain. And we took this cuboidal element and proved that the volumetric strain is the sum of these three displacement gradients, which we expressed as divergence of the displacement field. Now, analogously we can relate the volumetric strain rate to the velocity gradients. Let us see how do we do that. First, let us define volumetric strain rate. For volumetric strain, it was change of volume per unit volume, and so the volumetric strain rate is rate of change of volume per unit volume. This definition we have seen just now for volumetric strain as fractional change in volume, which we have seen as the sum of these three displacement gradients. So, now analogously for the case of fluids, the volumetric strain rate, which is the fractional rate of change of volume. Okay. So, volumetric strain is change in volume per unit volume, and volumetric strain rate is rate at which this happens. Okay. So, rate of change of volume per unit volume or fractional rate of change of volume, okay, both are equivalent. Just like we had some of these three displacement gradients, we will now have some of these three velocity gradients, okay, dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z. Okay. Just like in the case of normal strain rate and shear strain rate, we had for the case of solids, for example, normal strain in terms of displacement gradient, left hand side normal strain became normal strain rate, right hand side became velocity gradient. Similarly, here we have volumetric strain in terms of displacement gradient, and so volumetric strain rate in terms of velocity gradient. Same expression, replace the displacements with the corresponding velocities. And just like we expressed the fractional change in volume as divergence of displacement field, we can express the volumetric strain rate in terms of divergence of the velocity field. So, now we have come across divergence of velocity earlier. Once again we are coming across divergence of velocity. So, now there are two viewpoints or two ways of discussing the physical significance of divergence, and so we are going to discuss the physical significance of divergence from two viewpoints. That is the objective now. As we have said, divergence of velocity has two physical significance. What are they? First, we derived the continuity equation, and express that in terms of vectorial form in this way. What is the significance of the two terms in the continuity equation or the differential total mass balance? The first term represents time rate of change of mass per unit volume. Second term either vectorially as divergence of rho v vector or sum of these three terms, that represents net rate of flow of mass out by convection per unit volume. Okay. So, divergence of rho v vector represents net rate at which mass flows out by convection per unit volume. So, if you take del dot V, if you take out the density and if you consider only del dot V, that represents net rate of flow of volume of fluid. Here in this case it was mass, because we have only del dot V. So, it represents net rate of flow of volume of fluid, once again leaving by convection per unit volume. In the case of del dot rho V, it was mass, del dot V same physical significance, instead of mass it is volume. Okay. Okay. Now, this gives physical significance of del dot V from an Eulerian viewpoint. We have a small region and del dot V represents net rate of flow of volume of fluid leaving by convection per unit volume. Okay. Now, we have seen an alternate viewpoint for del dot V in the previous slide, which is fractional rate of change of volume. So, we can interpret del dot V also as fractional rate of change of volume. Okay. What does it mean? If you have a fluid element, and let us say if you are following the fluid element, the rate of change of volume of that fluid element, of course per unit volume, is represented by del dot V. So, another physical significance of del dot V is that the rate of change of volume of a fluid element as you follow the fluid element, of course normalized per unit volume, and this viewpoint, this significance of del dot V is from a Lagrangian viewpoint. First one was in terms of an Eulerian viewpoint, this physical significance is from a Lagrangian viewpoint. So, del dot V can be expressed both from an Eulerian viewpoint, which is what we already discussed when we discussed the continuity equation. The new viewpoint is from a Lagrangian viewpoint, and that is the fractional rate of change of volume of a fluid element. Why is it Lagrangian? Remember when we discussed about normal strain rate, shear strain rate, similarly volumetric strain rate, all the derivatives are substantial derivatives, capital D by dt. So, all the derivatives are following the fluid motion, and that is why del dot V, the fractional rate of change of volume, represents that we would observe if we follow a fluid element. Okay. Now, having understood del dot V, the divergence of velocity vector in two different viewpoints, what we will do is express the continuity equation from a material particle viewpoint. Actually, we have done this earlier for the linear momentum balance. This slide is a recall slide. We derived the linear momentum balance from a Eulerian viewpoint and then did some simple rearrangements on the left hand side, did some simple rearrangements for the terms on the left hand side, and that is what is shown here. We applied a product rule and then grouped terms together, used the equation of continuity, and then the left hand side was represented in terms of rho into acceleration of fluid particle. So, we re-express the linear momentum balance from a material particle point of view. Why is that? The left hand side is now in terms of mass per unit volume times the acceleration of the fluid particle. So, the left hand side now is in terms of a Lagrangian viewpoint. So, the same linear momentum balance we expressed from a material particle viewpoint and discuss the significance as well. And now, what we are going to do is express the equation of continuity from a material particle viewpoint. So, let us look at the Eulerian representation. So, this is the equation of continuity which we have derived when we derived the conservation equation for total mass, the differential form of that. You can also express the continuity equation in terms of divergence. And what is the significance? The first term represents time rate of change of mass per unit volume. Second term represents net rate of flow of mass out by convection per unit volume, that we have seen again also. How do you represent the Lagrangian form? As we have done for the linear momentum balance, we take the, remember when we do in material particle viewpoint, when we express the linear momentum balance in material particle viewpoint, we rearranged the left hand side only, the transient term and then the convection term. Right hand side was still the sum of forces acting. So, let us take the equation of continuity. Let us apply a product rule. So, we expand all the derivatives, rho dou Vx by dou x plus Vx dou rho by dou x, and similarly y direction, similarly z direction. So, let us group terms together. First we have dou rho by dou t, and then let us collect these terms, these three terms, and they are written here, and then rest of the terms are written here where rho is a common factor. Let us rewrite that last equation here, and then we will be able to easily identify terms of physical significance. Okay. We will do a small rearrangement so that we can write the physical significance of the terms. Okay. So, we take this term to the right hand side and then bring density to the left hand side, and that is why this is minus this term. Okay. Now, we can easily identify that these four terms together constitute the substantial derivative of density. Okay. So, 1 by rho d rho by dt, and this is very clear, it is divergence of velocity field, okay. And of course, you have a minus sign. So, what we did is took the continuity equation which we have derived, applied product rule, simple rearrangement, and then we could express the continuity equation from a Lagrangian point of view or a material particle point of view. Why is it Lagrangian? Because we have d rho by dt on the left hand side, which is substantial derivative, which is derivative following a fluid particle. Okay. So, in terms of significance, what does the left hand side tell us? Fractional rate of change of density of the fluid particle. Why is it fractional rate of change of density? We have d rho by dt is rate of change of density of fluid particle. Why is it? Because it is d rho by dt. It is fractional because we have 1 by rho. So, left hand side represents fractional rate of change of density of fluid particle. Right hand side we have seen just a few slides back that del dot V represents fractional rate of change of volume of fluid particle. So, now look at the significance. both the left hand side and right hand side corresponds to a fluid particle. Left hand side represents fractional rate of change of density, right hand side fractional rate of change of volume, of both correspond to a fluid particle. Okay. So, as you follow a fluid particle, what is its rate of change of density? Okay. That is what is given by this equation of continuity expressed in this form. Okay. Okay. So, what does it imply? Change in density of fluid particle. So, when you look at this equation of continuity, you should imagine that we are following a fluid particle and looking at its rate of change of density. So, change in density of a fluid particle is entirely due to changes in its volume. Okay. Because of change in volume, its density changes, or density changes are attributed to the change in volume. Okay. Now, if the volume of fluid particle does not change, what does it mean? You are tracking the fluid particle and the volume of the fluid particle does not change. What can we conclude? If you look at the right hand side, the fractional rate of change of volume, which is del dot V, which is sum of these three velocity gradients, is equal to 0. Okay. Then of course, the flow is incompressible. Okay. So, this is a very physically meaningful definition of incompressible flow. What is that? If you follow a fluid particle and if its volume does not change, then we say the flow is incompressible. What is the condition? Del dot V is equal to 0. How do we write that? We have seen the significance of del dot V as fractional rate of change of volume of a fluid particle. So, when that volume change is 0, then del dot V is 0, then the flow is incompressible. Okay. And we already discussed incompressible flow. So, let us compare both the conditions. Okay. This slide is a recall slide which I discussed already. This is the continuity equation, the significance of that, and then we discussed two special cases. One is for steady compressible flow, but the case which is relevant to the present discussion is for incompressible flow. We said for incompressible flow, density is not a function of time or space, and so what happened in this equation, dou rho by dou t was 0, and because rho is not a function of spatial location, you could take out, and so you got dou v x by dou x, dou v y by dou y, dou v z by dou z. Sum of all these gradients is equal to 0 or del dot v equal to 0. The same condition which we have discussed now, the same condition which we have discussed now as del dot v equal to 0, and we said rho is not a function of space or time, which means d rho by dt is equal to 0. So, both the conditions are equivalent. First we said the condition for incompressible flow in terms of density, density not varying with time or space, and hence arrived at del dot v is equal to 0, and we said that is a incompressible flow. Now, once again we arrive at the same condition, del dot v equal to 0 in a more physically meaningful way, because del dot v represents rate of fractional rate of change of volume of fluid particle, and if the volume does not change, then it is incompressible flow. And when del dot v equal to 0, from this equation capital D rho by dt is equal to 0, which is in line with our earlier condition that density is not a function of time or space. So, we have discussed the condition for incompressible flow in two different ways.